Right. So anyway, so let's jump into the topic. And so I guess that this is not un, unfamiliar idea. What's going on? Yes, but I couldn't click. So just it's not moving. What's going on? Oh, okay. Okay. Well, and so it's not okay. So let's go back to the very start of type checking or type inference. The problem was that okay, so people developed a type theory or the programming language that's complicated enough that we cannot really do type inference in a finite time. So it's not a decidable question anymore. So for example, the system F is the type checking problem in system F is just undecidable. And this problem kind of tell us that going to a full type inference is not the way to go. And so nowadays, we kind of get used to the fact that we need to give some type notation to the terms that we are writing down. So that is also useful for documentation purpose. And so so here is the idea. So instead of just going instead of just infer the type completely, we can give some type notation to the programs. So that can be used for the compiler or the program for the language to check your types. They use this existing information to do this to help you to complete the type checking process. And so the basic idea is that, okay, so instead of just one single function for type inference, we have two kinds of function. One is to do type checking, another one is to do type inference. And here I use synthesis because this just to emphasize that we use certain information previously known to help us to get the type, to derive the type. So I use a different term to just make sure that we have that's a kind of different idea. Okay, so let's see, where's my okay, so yeah, so we have the synthesis and checking. So and so and also we to have these two different functions, these two process. We design the type systems to make sure that design the type system with two different judgment form and to do the jobs. Okay, so but I'll go into some more details, but I have to say that this technique, this idea has been applied to many different languages, even dependent type languages, and also in so like in some proof of systems. And so let's start from a very simple thing like simply type lambda calculus with annotations. Okay, so that's a typical definition or typical set of judgments to describe STLC, simply type lambda calculus. And we have these three is the most common one, and we also have annotation. Annotation is just say, okay, this term has this type, so check this for me. And to go from the bidirectional one or the typical one to the bidirectional variant, we basically annotate the information for. We'll say annotate what information can be can be synthesized or what information need to be given, to be checked. So for example, if you look at the variable rule, and typically what we do is we just look up the variable in our context, right? Then we can know what type of this variable is. Okay, so the information about this type A here can be derived from the context. So this one it gives us a synthesis mode or synthesis judgment. And next one is this. Given a term with the notation A, then since we already know that this type is A, we can use this information to check the type of T if that's really A. Okay, if that's the set, then we can return to the user that okay, so you are right. This term with this notation has the type you specified. Okay, so the idea is also okay, yes. Oh wait, okay. We can ignore the last two judgments for now. We come back later, but okay, probably you see some idea. And since we have two different judgments, we kind of say, okay, if you can derive this information, you can derive this type, then we can, and you want to check if this is the right type. So for example, if T here, you want to check if that's type A, but you can actually synthesis the type, and you can do that and check if these two types are the same. Okay, if they are the same, then you can say okay, yes, that's the right type. So that gives us the ability to switch between not switch between, but the switch from this synthesis judgment to this checking judgments. Okay, so that's the kind of basic idea of bidirectional typing here. Okay, so although this kind of systems is mostly presented with two judgments, one for checking, one for synthesis. So okay, yeah. So typically that's a typical idea. Okay, so we have two different modes, and you say okay, where to go and two judgments. But essentially, I think it's better to think of these two judgments as one judgment, but just with an additional index to say what is the mode of these judgments. So I will come back to this later, because when we describe what bidirectional system is, this will be helpful. But for now, we can just say, okay, so instead of two judgments, it's really just one judgment with additional index. And so once you have a bidirectional type system, or say a definition of language with these two judgments, and how you decide the type checking and type synthesis function. Okay, so you can start from untyped term T here, and perhaps with scoped, with its scoped. So for now we start with the scoped terms, but it's fine if you want to start with untyped and unscoped terms, and we can separate this different process into two. But anyway. And so in order to do the type synthesis, we want to build the type derivation for that term T. We can start to build the derivation for this bidirectional system and forget about the modes. Then that's okay. Then that's it, right? But actually, there's one more step. Later we'll see. Okay, but okay. So the question is how we define these steps once we have this definition. Okay. And so there's one more condition for bidirectional type system. It's not every bidirectional type system has can be derived type synthesis function process, but we need to know that the information flow does not get stuck in between. So that means that although we always specify what needs to be given and what needs to be synthesized, then but also make sure that everything we use to check in the premises need to be known or derived somewhere already. So for example, if we look at the this judgment, for this lambda abstraction. So this has a check-in mode in its conclusion. So you can expect that the user or somewhere will get this information in the bool from this conclusion. Then we can use this information in the bool to give the type of this variable x. And also because we know this the codomain is a bool, then we can use this to check the type of t here, and then we complete we kind of complete the information for this particular construct. Okay, but if we have a synthesis mode in the conclusion, this application, we want to synthesize something, then we'll start from the premises and try to synthesize, try to derive some type information. And if the type you derive is actually an function, okay, then we will know the domain, the codomain, and we can use this information again to check if the argument has the right type. So in this case, it's an int. Okay. So the idea is very clear. Okay, so what is how the type information should go, and how everything that needs to return needs to be derived somewhere. Okay, so so this is always a common from Yana Dongfield and Neil Krishna Sopani's paper, a survey paper on bidirectional typing. And the basis say, okay, so if you have this condition, mode correctness means that the type information, the flow of type information does not get stuck. And the system, if the system is also syntax directed, but we also can ignore this for now. And then we can simply just read off the implementation from the rules. Okay. So it sounds like it's a very easy idea, and it's very easy to implement. Now the question is, what is mode correctness, or what is bidirectional typing precisely? And the question about the mode correctness is, okay, so obviously, apparently this is a property about some language with two judgments. And okay, so what is, so the question, okay, so we want to specify this property and want to, then we need to know what is the language first. Okay, so if you want to have a language first, then the question is, what kind of languages are we talking about? Right, so it's kind of unfortunate that we don't have a universal notion of programming languages or languages that everyone agree with. And so there are different proposals how we can define a programming language or even define a criteria anyway. So we have so many choices. And so in the talk and in our work, we decided to use the simplest one. This is called, we called this as bidirectional byte signature. So basic idea, okay, I'll show you the idea, but because we chose this not because this is the most practical, but this is the language, the set of languages that we think it's easy enough to express the idea of bidirectional typing in a formal way. Okay, so and previously we only talked about this mode correctness condition vaguely to have this process. But the next one, so in the actual development, we'll we'll refine this process a little bit different. So we'll refine this with another step called mode declaration. So now we'll come back to this. I just let you know that it's not just a simple bidirectional type synthesis and one function defined one goal, but we are just split into two steps. Okay. So okay, so now you know the idea of bidirectional typing, and I'm sure that you have seen such implementations before. But in general, what is a language described by Bayesian signature? Right. So a language described by Bayesian signature basically consists of these three forms. The three judgments, we still have variable rules, we still have annotations, but everything else can be described by this one judgment. This is basically says that we have a construct for multiple arguments with their own context extension. So maybe look closely. So in this case, we first described the for the construct, we can describe the type of the argument and also the type of the term. So here is the so for this construct, every argument has its own types. Why that corresponds to like the abstract rule, the term itself has, for example, type B. So here will be just B, and the conclusion has a type, the function type from A to B, and here is the A0 is the conclusion type. Okay, and also need to specify the context extension. So I mean, how many variables you want to bind for that for each argument. For the abstraction, the only argument which only binds one argument and has its own type A, and here's the set of. But you can also bind more than one argument. So that's why this takes a context instead of just a type. Okay, and that's basically the okay. So we also have the type variables appears in your in a construct. So for example, in this case, we have two variables A and B, or two meta variables A and B. So to describe this kind of construct, it's enough to say in a very compact way, like okay, so we have, okay, so to describe the abstraction construct, we only need to know how many meta variables we need and the type of argument and its context extension, then the final is return type, okay? So that's the basic idea of Bayesian signature. And you can describe other constructs in simple time calculus with these kinds of signatures for each operation. Okay, please.
How should we interpret the square and rectangular brackets?
Square, this one?
Yeah, so for instance, the square bracket.
So this one means the square brackets is for the context extension. How many variables you want to bind and the type. And the B is the type of the argument or type of the premises for that judgment.
The angle brackets are the action of substitution, and row is a substitution which assigns actual types to the schematic variables, which are the things that are cataloged, assigned.
Okay. So that's the language what I'm talking about. So this basically has three judgments. It's even less than the simple type language calculus I talked about. So, but we want to go from on bidirectional or ordinary type system to bidirectional type system. We add, of course, one more judgment to switch from synthesis to checking. And how about these signatures? How do we describe other constructs? Well, that's similar. The definition is very similar, but with just additional index for each argument for your construct. Okay, should I stop here for a moment, or it's okay?
I guess my final question on this hopefully is where is row determined or bound? The
Yeah.
variable row in the rule, where does that come from?
Which one?
The row that passed everywhere. Yeah, the substitution, where does that come from?
When you construct the type derivation, you need to actually give the actual type for each type variables, right? So when you build the derivation, that's the installation of for each variable. So okay, so
It's explicitly given.
It's basically given, yes, and it's given internally so that you can give this as one rule. And I think, okay, so for more details, but and for typically, I think so typically for type judgment, if we have seen a variable, we can interpret that as a judgment quantified externally. So there are multiple judgments, but also we can interpret that as single judgment with this kind of installation inside the construct, inside the judgment. So it depends how you interpret. But in this case, we have one single judgment for each operation, and for the types, for each type installation is part of the construct. It's okay. It's internally indexed.
What does sigma contain?
Sigma with
substitution type formula, I guess.
Okay, so this is for the set of types you have.
I see.
Yeah. Yeah, but it's probably not okay. It's okay. Okay, so the bidirectional signature is not so different from the typical bidirectional signature. It just has one more mode for each argument and for its conclusion or the return time. Okay. Right. And so the good thing about this this system is we can now prove formally that the mode does not actually interact with the types, right? So we can prove that, okay, so if we have a derivation, typing derivation for bidirectional type system, you can split it into two derivation, one for the ordinary typing derivation and one with mode only. Okay, and that's good. And that also means that we don't need to check the bidirectional typing in one go because we can split in two steps. Okay, and this for now. First, okay. Okay. So we have seen, okay, so the correspondence also means there's some incomplete results between these two judgments. And from the untyped terms, we can build the modes for each type terms first, and to guide the type synthesizer what kinds of function we need to apply for this term, or do we need to check, or do we want to synthesize the type? So first of all, what is a derivation type? What is a valid mode for that term, and can be derived just by erasing? Okay, so the spec or the judgments for specifying a mode can be derived by erasing the types from the bidirectional type system. So we get something like this. So we don't have a type yet. Just say, okay, if the variable x is in the context, then we assign the mode synthesis to this term. If that is a notation, we give the a mode synthesis for this one. And similarly, we can do for other type of judgments, like the operations or other constructs. Okay. And why is that interesting? Because so intuitively we can prove that, but intuitively that if you if your program does not have enough notation to do the type checking, then it will not have the mode declaration, or will not have the right derivation, mode derivation for that term. So we can use this to check if we have been annotated enough. Okay. And right, and because of the completeness, we know that if it doesn't have a mode, if it doesn't have a mode, then it cannot be bidirectionally checked. and this condition, or this derivation, is simple enough that we can basically do to check if it has the right mode. It's just a decidable question. So far so good. Right. So now we have mode declaration to build the mode, to assign the mode for a term. Now, how do we, well, I don't have time to talk about the every detail, but okay. So that's kind of okay. So we haven't talked about any condition about this bidirectional type system. Everything works at this moment without any condition. Now, if you want to actually build a bidirectional type synthesis, then we need to define the mode correctness logically right now. But the basic idea is that we can kind of classify the meta variables in every operations or in any construct into known and unknown variables. Known variables means these can be given already from the conclusion, or they has been synthesized previously from other premises, right? So, but for synthesis, synthesizing conclusion, we don't have anything we know from the beginning, so I have to start from premises. So we start from kind of empty knowledge. But for the checking conclusion, we know it is something from the input, from the conclusion part. Okay. Right. And oh, sorry. Okay. And when we move our focus on the judgments, if we see a checking premise, or say a checking argument, then we need to make sure that every variables in that argument, every meta variable in the argument needs to be known from your context or from somewhere, right? And that's the basic idea of what I say here. Oh, I need to be known by the checking site. And if this is a synthesis, then only the context for that arguments need to be known. And the output, because you will produce the result you want. So it will synthesize the type. So we don't need to know anything about the output. So that's the basic idea of mode correctness. Okay, so now we can kind of define what the mode correctness is formally. But it's a bit hard to say. Time do I have? Yeah, but okay. So that's what I defined in the paper or in ACDAM. But this basically says what I have meant informally. So okay. So yeah. So once we have this. Once we have these conditions, and we have the mode correctness, because mode correctness ensures that everything that need to be that will need for our inputs already can be synthesized somewhere already. And so it's kind of easy to write down the algorithm, and we can prove that when we have a term with the modes, then it's just decidable whether we can do the corresponding operations in in a finite times. So for example, if the mode is synthesis, then decidable to construct some type for this terms, or we can give negation proof. Okay, and similarly, if this is a check-in, then you can give any type, and you can prove that okay, actually, this type is the type you specified or not. And yeah, but our reason will say the actual proof is actually very close to the typical implementation. So you look at if that's a variable, okay, just look up the context. And for others, but yeah, okay, and for other constructs, we need to do some more case analysis. But intuitively, this all very clear. But just need to do all kinds of possibility and do the case analysis and that. And I can show the exact code later, but it's kind of similar. Okay. Okay. And so we have now so far we have basically sketched what's going on with this bidirectional type synthesis. And okay, so of course if we actually derive a bidirectional derivation, typing derivation, then we can just forget the modes. We get the ordinary typing derivation. And on the other hand, if the bidirectional type synthesis says no, we don't have this derivation, okay? And but since we already construct the modes, the mode for these terms, then we can use these two facts to construct a negation for the ordinary typing judgment, right? So assume that D has a type A, but also because we have this mode, it also means that we have this bidirectional typing derivation, but that's a contradiction. So that's get this confidence. Okay. So yeah. So one thing that's also from the development is probably we shouldn't view type checking or especially bidirectional type checking, type synthesis as a decidable question, but more like a trichotomy that we have three possibilities for your term, for your untyped term. One is that it has not enough types, or it has not enough annotations, or it has enough annotations but is not typed, or it has the right amount of notation and it has a type. So that's the if we compose all the process together, we'll get this conclusion. So so what I showed here is okay. So more correctness now is a kind of formal condition that you can specify, and I'm sure that you can do it with a more complicated language. But also in our work, we didn't say how we should decide the system. That is a question that I leave to you, or you can maybe we can have some recipe to generate bidirectional type systems, but it's not the concern of this work here. And yeah, we can prove everything in ACDAN, and actually can show you that is the proof is actually a program that can produce the derivation. And yeah, about that. And there are some more sophisticated approach which uses a more complicated language, which is basically a logical framework with rewriting rules. And this done by Thiago Friesman. He actually described how we can do it with more complicated language, but with a catch that he has already specified the bidirectional rules for admissions and introduction rules. And so it's kind of it's very powerful, but not kind of biased towards some certain design choice. Okay, so that's basically the work I presented last year. But when I think about all of the work I've done so far. I found that something it's kind of afterthought is bidirectional typing really about typing it though? It's really about type system because the idea is okay. The idea is that it's basically the control of information flow, and for a simple function, you can always promote it to a relation, right? And if we have input index with output index, and obviously this is all kinds of bidirectional in a sense. And the reason why I talked about this decidable problem was this question is decidable. You can either produce witness or contradiction to the derivation because we have some certain decidable relation in between. So for example, when we have the context, we have to look up the context. So I've checked the membership. If that doesn't, if the type is not right, then we can, okay. So for the scoped syntax, for scoped language, the lookup always succeeds, but for unscoped terms, then the lookup function may fail. And also we have other decidable relation like we have to compare two types. Okay, we have to compare the given. So for example, if you for the abstraction rules, you have the function type, then we need to first check if the type is a function type. So we need to do some kind of unification or some problem to check if that's actually a function. And so if that fails, then the type checking process also fails. So this is a problem that we not only have, so bidirectional type system not only have has the flow of information, but also entangled with some decidable relations and propagating through the flow. So if some kind of function fails, then the whole process fails, but nothing to do with the information flow here, but just because some kind of decidable function is making noise. So so if you look at this again, so here's what I talk about. You will return to the types, and we need to check if this is actually the function type or not, right? And also, if this is unscoped syntax, then we need to check if this variable is in the syntax or not. And if it's not in the context, then we'll report an error or produce a contradiction from the bottom of the syntax from a variable to the terms you are tracking. Right. So maybe it's not really about bidirectionality. Maybe it's not really about type system at all. It's perhaps about inductive types, inductive definitions, whether this inductive definition is bidirectional or not. But it's just I haven't worked this out yet. So let's start here.